Welcome back to Linear Algebra. Today we'll introduce the concept of the change of basis matrix, and this is not to the standard basis. Okay, so let B equal B1 through Bn and C equal to C1 through Cn. They're both going to be distinct bases of some vector space V. Then we can write the vector x relative to C as the change of basis matrix times the vector x relative to B. So this change of basis matrix is going to be n by n, and what this says is it takes a vector relative to B and it maps it to a vector relative to C. So this is what the matrix will look like. So we've already seen this actually. So let's draw what we've seen. So we've seen B going to the standard basis. So what this looks like is this is taking B1 relative to E and all the way up to Bn relative to E. But the thing is, we know about the standard basis is that if we take any vector x relative to the standard basis, well, we just get x back. So when we do things to the standard basis, we just completely ignore all this notation. So we take away these brackets and these transformations, and we're left with something very familiar. So you've really already seen this before. So with that being said, let's jump right into it. So we're going to let B1, B2, C1, and C2 be vectors where the B's form a basis and the C's form a basis, and we want to find the change of basis matrix. So the easiest way we can do this is we can do some row reduction. So we can take a partition matrix where our vectors of C are on the left side and the vectors of B are on the right, and we reduce C down to the identity, and what we're left with is the change of basis matrix from B to C. Okay, so let's use this. So we want to set up our matrix, so we're going to have C1, C2, and then B1 and B2. Let's make sure the order is the same. So if you pick an order, make sure you keep the order. It's still going to work if you flip the order, but then you have to flip the order in everything you do. So going C1, C2, then B1, B2. It's good to keep things in order so you don't get confused. Okay, so let's just put these in here. So C1 is going to be 1, negative 4. C2 is going to be 3, negative 5. I'm going to keep the line in the middle just for the sake of it. B1 will be negative 9, 1, and B2 will be negative 5, negative 1. Okay, so the first row looks good. 1 to 3, negative 9, negative 5. We're going to add 4 of the first row to the second row. So we're going to have 0. We're going to add 12, so we'll be left with 7 there. And then we will be left with 1 plus negative 36. It's going to be negative 35. And then we're going to be left with negative 1 plus negative 20, so that'll be negative 21. At this point, I'm going to divide the second row by 7, so the numbers aren't so terrible to work with. So we're going to be left with 1, negative 5, and negative 3. And now what we can do is we can take the first row and subtract 3 of the second. So we're going to be left with 1, 0, this should be 6, and 4. Then we'll be left with 0, 1, negative 5, negative 3. So what we're left with is the identity matrix and the change of basis matrix from B to C. So that P from B to C is going to be the matrix 6, 4, negative 5, negative 3. Okay, so we can do this with polynomials too. So what I did here was I said, okay, C is going to be the basis 1t and t squared. Well, we know this is the standard basis E, but for the sake of it, I want to show you that this works if we don't label it as E, and we actually do the full reduction. So again, we want to set up so we have C on the left and B on the right. So C is going to look like 1, 0, 0 because that's what the 1 represents, the t represents the vector 0, 1, 0, t squared is 0, 0, 1, and then for our basis b, so 1 minus 3t squared is 1, 0, negative 3, 2, 1, negative 5, and 1, 2, 0. Oh, but look at this. We have I, so this must mean that this is p to c, or p from b to c. So we already have our change of basis matrix, and well, of course this is, because this is just going to the standard basis. So again, I really want to emphasize that you've already done this. So if you watched the previous video, you've already seen this, except instead of going to the standard basis, we're going to any basis we want. So for instance, if we want to draw a picture of this, so let's say this is our vector space V, and before we went to this space with the B transformation. So this takes some vector here, and it maps it to some vector in Rn, so this is x relative to b. Okay, so now what we're doing is we can say, well, we can also go to a different space here by some transformation relative to a basis c. Should make that look more like a c. And then we'll get some vector x relative to c here, and this is also going to be an Rn. So what we can do now is we can, instead of having to go back to the vector space V, then to the basis C, we can just go straight by taking the change of basis matrix from B to C. So this is kind of a general picture of what exactly is going on here. So before, this was our basis E. So really, we could just go back by taking P to E from B. So again, this isn't anything you haven't seen before. Try to make the connections, and hopefully on your exam, you won't be fooled by this. Okay, so if you have any questions, leave them in the comments below, and I will do my best to answer them.